Okay, it is now noon, so I have to start. Does anybody have any questions or anything before we start? So we're still in the intro to quantum mechanics, and we've covered basically talking about the electromagnetic spectrum, and now we talked a little bit about properties of light and about the wave-particle duality nature of things. Now we're moving on, we're talking about the wave nature of electrons. And there's something in physics called the de Broglie wavelength. We're not going to go over the proof for that. We're just going to go and state it. Do you want me to turn the lights off on the left side? Or do you want me to keep them on? Lights, okay. Needless to say, you get an equation here. And it's just given to you. The de Broglie wavelength is Planck's constant h over the mass, it's over the momentum, mass times velocity. So to figure out the wavelength of an electron, so we put in Planck's constant, 6.626 times 10 to the minus 34 joule seconds, all over mass. Mass is, the electron is 9.11 times 10 to the minus 31 kilograms, or 10 to the minus 28 grams, maybe you've seen it that way. But in kilograms, then velocity 2.65 times 10 to the 6 meters per second. And so if you look at the dimensionality, looking at the dimensionality of this, we have joule seconds over kilogram times meters per second. And joule is a Newton meter. It's a kilogram meter over second squared times, times meter, so it's meter squared times second, all over kilogram times meters per second. So the seconds here cancel, and the 1 over seconds cancel. I should use a different color to cancel things out. These, it looks too, I'll do yellow. So the seconds cancel, the inverse seconds cancel down there, meter cancels out the squared, kilograms. So, can't see that as well, but either way, the dimensionality is meters. If you follow through with all the units. So then this, right before class started, I put this up in the calculator. This is 2.74 times 10 to the minus 10 meters. They're like that. Okay. So 2.7 times 10 to the minus 4 meters. A hydrogen atom is about 0.51 angstroms, so that's about 10 to the minus 10. So it's about half the size of a hydrogen atom. So that's the wavelength, an electron at this speed. And notice the momentum here. So let's say you put a 120 kilogram mic and going that fast. My de Broglie wavelength is going to be really small. So instead of 9.11 times 10 to the minus 31 kilograms, I guess I'm 118 kilograms. 118 kilograms instead. My de Broglie wavelength is going to be about 10 to the minus 33 times smaller than that. Right? So we're looking at something times 10 to the minus 43-ish meters. And so a wavelength of a big particle like me is pretty much inconsequential. So something has to be really tiny in order for the Broglie wavelength to really take an effect. What do I mean by tiny? Protons, neutrons, electrons, small molecules. That'll work. Things like humans, staplers, baseballs, it doesn't really matter. The de Broglie wavelength is too small to even take any effect whatsoever. So that's why we don't exhibit wave-like properties, because we're too big. But okay, for this one though, we are given an electron with a certain velocity or speed, and we already know the equation, the de Broglie wavelength. Lambda d is Planck's constant over the momentum. Plug in the numbers, and we get something close to half the size of a hydrogen atom. And dimensionality meters. Anybody have any questions on how to do this one? All right, why don't you try this one out? What is the velocity of an electron? Now I flipped it on you. What is the velocity of an electron if the de Broglie wavelength is, what's that? You can probably see this better. Lambda d is h over momentum. Oh, no. Times velocity. Oh, and mass. I know it. I covered it up. You don't have to do all the units if you don't want to. I mean, noting if you put everything in kilogram meter per second, it'll all work out properly. Is anybody stuck? Raise your hand if you stuck. So how do you think A, 3 by 6 meters per second? We think B. How many think C? I think D. So we got a third of the class going for B, but the rest of you are confused. I'm going to come around and see what you're doing. Is anybody stuck? Need any help? Yes. So,
That it?
yep. That's great.
Are you confused on the answer?
Is it? Yeah. Did you say it's
Yeah. Okay. Oh, you got it. There you So hopefully you got the answer B. I was going around, seems that way, but I pardon the extra effort on my part. It's called a psychomotor skill. You know, psycho brain motor doing something. Calculators, putting numbers in the calculator is a skill. So, does anybody have any questions with this? Okay, next thing. So, if you've heard of, this is Heisenberg's uncertainty principle. You probably heard of Heisenberg from Breaking Bad. So, this uncertainty principle, it's a mathematical construction. It's based off of linear algebra. But the uncertainty principle is the change or the uncertainty in the position times the uncertainty in the momentum is greater than or equal to Planck's constant h over 4 pi. You might also see something like this. If you ever see h bar, this is h over 2 pi. So if you ever see the term h bar, that's Planck's constant over 2 pi. So you might see the uncertainty principle as h bar over 2. But what this is saying is that we can only know the position or the momentum of something so much. So quantum mechanics works off of 7 dimensions. So there are 3 dimensions for position. So if you have a point in space, we have 3 dimensions to describe where it is, the length, width, and the height, if you will. So just 3 x, y, and z, or you can do x, y, and z this way. Either way, you have a point, and you have x, y, and z to describe where that point is. So that's 3 dimensions to describe where the point is, and then it's where it's going. So if you have a point, if it's moving this way, that way, that way, that way, then there's 3 dimensions to describe where the point is going. That's the momentum. And anybody want to guess what the 7th dimension is? Time. It's not curling. That's string theory. So time is the last dimension for quantum mechanics. So, and this is also in part by how you probe something. So by probing something, you can actually change the nature of it. Meaning, if you analyze something's momentum very well, you have no idea where it's at. And if you figure out where something is at, then you have no idea where it's going. So there's an old joke saying Heisenberg is speeding along back in good old Germany in 1930 or something, and a police officer pulls him over and says, "Mr. Heisenberg, Professor Heisenberg, do you know how fast you were going?" And he goes, "I know where I am." And so the idea of yeah, chemistry humor is pretty rough, I know. But the whole point of that is, he says, "I know where I am." That means he has no idea how fast he's going, or his momentum. This also works, the uncertainty principle also works for energy and time. So, and this is a real effect for laser pulses. So you can have laser pulses that are really, really short, so down to attoseconds. And the thing is that the photons, the laser pulse is really short, but then the energy spread of the photon is just huge. So, and you, meaning it's from like ultraviolet to infrared. I mean, it's the laser pulse does not have a set frequency or energy. And there's also, I think this is kind of cool. I guess I shouldn't talk too much about it. There's something called Feynman diagrams. Have you ever heard of that? So the thing with change in time, the uncertainty in time, you can actually get processes that happen before they're finished. So for instance, a mirror, the way a mirror works, you have silver on glass. And so if I look at my face in the mirror, the light shines from my face, the image gets reflected off of my face to the silver metal that's on the mirror. And then what happens is the light waves from my face go to the mirror, then the light is absorbed by the mirror and then emitted back. That's the reflection. It's actually a photon in, photon out process. And then my eyes can see the image. So because of the uncertainty principle, though, you have three different things that can happen. You can have, so if you have time, so where do I write this? If you can have, so time going up, you can have the photon come in, it's absorbed, photon comes out. You can have the photon come in, it can wait a bit, and then it can go out. You can even have the photon go out before the photon comes in. So you can actually have processes where the effect happens before the cause. But it only works on really, really small timescales. Really, really small. But that's something called a Feynman diagram. But if you want to know more, we can talk about it after class, or you can look at it on Wikipedia, or there's a lot of comics. If you ever look at PhD comics, I like that comic, or XKCD. Does anybody like XKCD? No one looks at those comics? Okay. That's they're nerdy comics. They'll sometimes mention that stuff. But okay, so back to the uncertainty principle. So we're not sure of where things' position or momentum is, where things are, or where they're going. So this is a classical trajectory. So classical trajectory is like taking a basketball and throwing it. So if you take a basketball and you throw the basketball, what happens? It goes into a parabola, right? And the basketball follows that parabola coming down. What would happen if I were to chuck an electron? There would be a probability. Why is there a probability? Because we're uncertain. We're uncertain of its position momentum. Now, a common misconception is that if you have an electron here, it's just dancing around. It's actually in all those places at the same time. It's not like it's just in one spot and it's dancing around. It's actually in several different places at once. unless you try to find it. If you try to find it, then you can find it, because then you find its position. But then if you do that, you have no idea where the electron is going, because you have no idea where the momentum is. Likewise, you can figure out the momentum. So in this diagram here, as written, it looks like you're really keying down its momentum. Since you really know where its momentum, where it's going, you have no idea where it's at. But those are usually in extreme cases. Usually we don't like set one or the other. An electron, in an experiment you do, but electron's not always being probed. It's just doing its own thing. So if you want to know what an electron, at least what I think an electron looks like, I think they look kind of like footballs. Like a football with a, if I think of an electron going through space, I kind of see it like a football, but then a probability. So like it's probably mostly around here, not so much around the edges, and it's football shaped because it's usually going somewhere. If it's sitting still, then it's more spherical. But if it's going somewhere, it tends to elongate. And if you take an electron, you throw it into a particle accelerator, and it goes really close to the speed of light, the electrons themselves get really, really flat and thin. They're almost like super flat pieces of spaghetti. And when that happens, they also, because their time is so spread out, you can stack them on almost nearly on top of each other. It's like electrons, like our hands and everything else is made. The electrons are what pushes back, right? I can't really flatten my hand together, but if you took the electrons and put them in a particle accelerator, you could they couldn't stack them up, but you could get them really close to each other. So you can get a lot of matter in a really small beam that way. Okay, so let's go back and talk about some of these effects, the uncertainty, position, momentum. So this is the probability distribution right here. So the analogy is a strike zone, that a lot of stuff happens in the middle, not so much around the edges. So it's more likely if you're hitting something. This is just another way to look at it. Funny thing is, I think I think better in quantum mechanics terms than classical mechanics terms. It's hard to switch between one or the other. And okay. So now moving on, maybe you've seen this before, the Schrödinger wave equation. So the Schrödinger wave equation is simply this. It looks easy. H psi equals E psi. So this is now, I'm trying to explain this now. This is not on the test, but this is something you can learn later on. There's much more math, much more things involved. So the H is a Hamiltonian, psi is the wave function. A Hamiltonian is known as the operator. So in this case, the Hamiltonian is specifically the kinetic and potential energy of the electron. And the energy of the electron operates on the wave function, and then the energy levels are spit back out, and then you get the wave function back. Is anyone here taken linear algebra before? So do you know what an eigenvalue is, an eigenfunction? Okay, you haven't gotten there yet. These are the eigenvalues of the matrix algebra. So, and I said an operator. So these are operators, plus, minus, multiplication, division. So if you say 1 plus 1, you know that the plus sign is an operation that tells you to add them. And 1 minus 1, that's a different operation than times 1 or divided by 1. So these are operators. This is an operator. The Hamiltonian, the energy is an operator on the wave function, and it spits out specific energy levels. And that's the discrete math. I mentioned discrete mathematics. There are only specific energy levels that exist. Some people look at me like deers in the headlights. Some of the stuff, and this is the super advanced background to it. I'm going to go over the quantum mechanical model in a second, and I'll explain it. It'll sound really confusing, but it's one of those things when you leave and then you go take a nap or sleep tonight, when you wake up, you're like, oh, that's starting to make more sense. So this is going to be one of those lectures and you're like, what the heck was that? And you might see orbital shapes. So I'm going to show those. It depends on how much time we have. We can talk about orbital shapes. If you wonder where those come from this. This is the integral from negative infinity to infinity of the wave function vector dotted with the complex conjugate of the wave function over d tau. D tau is just all space. So if you take a wave function and you integrate it, the vector dot product of the wave function times complex conjugate over all space, then you get kind of what it looks like. It's probability density. And the complex conjugate, so what is that? If for a complex number, if you ever heard this, you have real numbers. So then a complex number is a combination of real and imaginary. Imaginary is just something to I. I is the square root of -1. I to a non-real power of I. So if you have 3 plus 2i, the complex conjugate is 3 minus 2i. And imaginary numbers, it's not like, all it is it's a flaw in our number system. Okay, mathematics is a very powerful model. It works extremely well. It has inherent flaws, and one of them is imaginary numbers. The other thing about imaginary numbers is that it causes things to be cyclic in nature. So imaginary numbers are important because so you have I squared is -1. I cubed is minus I to the 4th is 1. I to the 5th is the same as I is I. So it's the cyclic nature of things. And actually imaginary numbers are also how we can get sines and cosines and that kind of repetitive functions from imaginary numbers. So it's not necessarily I is just some weird thing. It is weird, but it gives to the cyclic nature of mathematics. So, but this is stuff all later, and there's even a better way to do it than this, something called an electron level function. At least 20 years ago they were developing it still. So we're working on new and better ways to do this, but the pictures you see are from this. Okay. So that's above and beyond this course. So let's go back to what this course is. The wave function is solved for the hydrogen atom. We can solve this, and Schrödinger did this. He did this supposedly in a weekend trip with his mistress, as the legend goes. And the energy levels for an electron in the hydrogen atom the energy level is negative 2.18 times 10 to the minus 18 joules, 1 over n squared. Okay, so a couple of things. These are also known as Rydberg states. So you heard the word Rydberg states or Rydberg equation. So if you do, I don't know how many of you go and read other stuff outside of class. So you won't see that written in the textbook, but this is known as also Rydberg states. And that's the Rydberg constant, the minus 2.18 times 10 to the minus 18 joules. You can also see the Rydberg constant in wavelengths as well. You might see it in inverse nanometers instead of joules. And we get this saying that a free electron, so imagine the football going through space, that free electron has 0 potential energy. So it has no potential energy, but then a bound electron has negative potential energy. So the potential energy is relative, and we pick a free electron as having 0 potential energy. So, and this works for all atoms. Can you imagine if we did it the other way? Say we picked carbon-12, the 1s orbital, as the 0. Then we'd have to relate everything to that electron. And then we'd have to do 2 calculations. So we'd have to relate it to the ground, to 0. Then we'd have to relate it to carbon-12. So it's just a way of making the math easier. So we pick our 0 that way. Okay. And I know I might be confusing you. I apologize. Let me keep on talking. But keeping on talking, we have this e to the n is n squared. So, and this is the quantum mechanical model for the atom, by the way. So now we begin. So n squared, e to the n, and they have n squared. N is known as the principal quantum number. And n, this sigma means exists, n exists as whole numbers only, positive whole numbers. So n cannot be 0. N can be 1, 2, 3, 4, 5, 6, on into whole numbers to infinity. So that is how n exists. Now I'm going to introduce a new quantum number, the angular momentum quantum number. I'm going to call this L. And L exists as, can be 0, n cannot be 0. L can be 0, 0, 1, 2, 3, on to infinity, but is bound by the principal quantum number -1. Okay, so n can be positive whole numbers and 0. N can only be n can only be positive whole numbers. L can be positive whole numbers and 0. Because if n is 1, L is 0. But if n is 2, L can be 0 or 1. If n is 3, L can be 0, 1, or 2. Up to, if it's 3, it can be up to n minus 1. Now the next one is, oh, and here's some things. If L is 0, we say that that orbital is an s orbital. So what is an orbital? This is going back to the Bohr model. Maybe you've seen the Bohr model looks like this. You ever seen, and they show this for a lot of pictures. So if you have atoms that are like, maybe you've seen something like this where you have electrons in orbits around the nucleus. Stupid lawnmower. That's not how atoms work. Atoms are not orbiting. Okay, but the Bohr came up with that, and the idea of shells, and it works pretty well, but it's not the end story. Quantum mechanics right now is the best model that we have for the atom. But the orbits, the name stuck, so we call these orbitals. So if our L is 0, we call this an s orbital. L is 1p, L is 2d, L is 3f, and those stand for sharp, principal, diffuse, and fine. So those are old spectroscopy terms. So because S are the sharpest peaks, and diffuse and fine, like principal, they're not as sharp as the sharp peaks, but they're still pretty prominent. Diffuse and fine, it's hard to see D and F. It's much harder to see the structure of those in an electronic spectra of. It's easy to see in the hydrogen atom, but if you look at like lead, it's really hard to see the F orbitals in that. Okay, and moving on, we have the magnetic quantum number, and the magnetic quantum number is equal to, L can exist as -L plus 1 on through 0 up integer steps through L. So m sub L is an integer. It can be negative, can be positive, and includes 0. So 0 is considered an integer. So n is only whole numbers, L is 0 and positive integers, m sub L is integers, but bound through negative L and L in whole steps. So meaning, if n is 0, L is 0, m sub L is 0. If n is 2, L can be 0, 1. If L is 1, m sub L can be -1, 0, or 1. If n is 2, if L is 2, then m sub L can be -2, -1, 0, 1, 2. One more, why not? If L is 3, m sub L can be -3, -2, -1, 0, 1, 2, 3. And the last quantum number that's not included until chapter 8 in this book. I include it now because we're talking about quantum mechanics. Last one is the spin. And for an electron, the spin is either plus or minus 1/2. So what is the spin? The spin is the projection of the magnetic moment of the particle. So which means is you have electrons, so imagine this football going through space. Actually, it's easier. Think of an electron with 0 kinetic energy. So it's an electron, it's a sphere, it's sitting here. At any point in time, the magnetic field of the electron is pointing in some direction. That's the spin. The spin is if it's pointing up, it really moves all around. It doesn't sit still. But the spin is the magnetic field overall is pointing in one direction. It's pointing in many different directions, but if you look at the entire vector field of all the magnetic properties of the electron, it will predominantly point in one direction, and that direction is what we call the spin. And electrons are known as fermions. So maybe you've heard of fermions and bosons, maybe you haven't. A fermion is a spin that is a combination, a division of two integers. That's not an integer itself. Like, I know that 2 divided by 4 is, actually no, 2 divided by 2 is 1, right? So that's a spin of 1, right? That's a combination. But that's not a fermion. A boson has an integer spin. So photons, for instance, photons are bosons. And electrons, protons, and neutrons are fermions. So now that leads us to the next point, the Pauli exclusion principle. Pauli exclusion principle says no two fermions may have the same set of quantum numbers in the same atom. So you can have electrons with the same set of quantum numbers, but they have to be in different atoms. There's only room for one, as they say as a quantum number, and this is the reason why matter has structure. So photons are bosons. Bosons have integer spins. There is no structure. There's no outward structure to bosons. Fermions, at least matter made of fermions, has structure. So that's why I can't put my hand to the desk. And what's going on is the electrons in my hand populate, and later on we'll learn something called the Aufbau or the Billionet principle. So they populate at increasingly higher energy levels, and they do so to the lowest state. And then then because of that, the atoms, the energy levels have structure in them. And if you try and put another electron, like take the electron on the desk and put it close to the other electrons, what happens is they push back. You're like, nah, you can't occupy my Macaulay exclusion principle. You can't occupy my space and time like that. And so there is a pushback. In fact, this is known as electron degeneracy. So I can push off the desk because of electron degeneracy. Maybe so stars, so white dwarfs and brown dwarfs stay stars because of electron degeneracy. There's enough gravity, but there's enough force pushing them back. If a star becomes too massive, it can break electron degeneracy and become a black hole. Then the electrons can be, you can break this, but you have to have something as massive as a black hole to do it. So, of course, that doesn't happen all that frequently. Okay, so Pauli exclusion principle, we'll talk more about this later, but also with this bosons, so you can get, bosons can be in the same place at the same time. So as I mentioned that electrons are in many different places at once, bosons can have the same set of quantum numbers in the same conditions. You can, in a single point, you can stack as many bosons as you want. So light, you can put all the light you want in a small space. Does not bother you. You can put, so I've done this with lasers. I mean, if you focus lasers down and you can just, using the light, you can focus it, and it can get so fine, it starts to, you can see it in the air, it starts to break, it starts to snap in the air because there's so much energy there. This is part of the thing with the Big Bang Theory. You're wondering, how can the whole universe be in one single point? It's all boson. If it's a boson, it could be in one point. There's certain parts of bosons. There's the Nobel Prize was awarded a couple years ago in University of Colorado. They took ruthenium nuclei. Some nuclei are bosons, and they've gotten bosons that are matter to occupy the same space at the same time. That's known as a Bose-Einstein condensate. So whereas I can't go to the desk, but if I turn into a Bose-Einstein condensate and the desk was, yeah, we could overlap. We would just kind of together. It wouldn't be a problem. No structure there. we believe that's how superconductors work. So superconductor is when electricity flows without resistance. So we think what's happening is two electrons join together, like two plus 1/2 electrons join together to form a dual electron with a spin of 1. So plus 1/2 equals 1. That becomes a boson, and then the electrons turn to bosons, and then since they can overlap, the Pauli exclusion principle doesn't work anymore. So then the electrons just all kind of jumble up together and they flow without resistance. Otherwise, if they're fermions, the Pauli exclusion principle holds, and then what resistance in a wire is it's friction. The electrons rubbing up against each other. So, okay, but again, much of this is above and beyond this class. Let's go back to the quantum numbers, and here we go. Principal quantum number, and the principal quantum numbers we'll learn next chapter. Those are the rows on the periodic table. The periodic table is described by the quantum mechanical model. These are the rows in the periodic table. Angular momentum, so the first two columns, the alkalis, alkaline earths, those are for the L equals 0, the s orbitals. The p block, the nonmetals, right, the boron, carbon, nitrogen, oxygen, fluorine, neon, that's the p block. The d block is the transition metals. The f block are the rare earths and the actinides. So, and also for the s orbitals, the L equals 0, why are there 2? So because m sub L, if it's n is 0, L is 0, actually let's go back to L. L is 0, m sub L has to be 0. There's only one orbital. Spin plus 1/2 minus 1/2, that's why there's 2. For L equals 1 for P, you can have -1, 0, and 1, so there's 3 orbitals. Then with its spin plus 1/2 or minus 1/2, that's why there's 6 in the P block. So then L equals 2, -2, -1, 0, 1, 2, that's 5. And then the 2 from the spin, there's 10. That's why there's 10 blocks in the D part of the periodic table. And similar, that's why there's 14. So the 3, -3, -2, -1, 0, 1, 2, 3. So that's 7. So 3, -3, -2, -1, 3 there, plus 1 for 0, plus another 3, 7. That's why there's 14 elements in the lanthanide-actinide series. So 7 orbitals and then the 2 plus 1/2 minus 1/2 spin. So that's where we're moving next. And this is real. I just thought this was cool. I was reading this, I'm like, what the heck? It's kind of cool. And it seems so simple. So complex at the same time. Okay, so let's use this knowledge. What are the names and the numbers and names of the n equals 4 principal level? How many orbitals are there? So n equals 4. So we've a couple cases. L equals 0. M sub L has to equal 0. So we have L equals 1. So M sub L would equal -1, 0, or 1. So we have L equals 2. M sub L can equal -2, -1, 0, 1, and 2. And then L equals 3. M sub L can equal -3, -2, -1, 0, 1, 2, 3. Okay, so how many, so what are the names? This would be the 4s, this would be the 4p, this would be 4d, and this is 4f. And how many orbitals are there? There are 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11, 12, 13, 14, 15, 16. So 16 orbitals, which also equals n squared. That's always true. Number of orbitals is always n squared. So if you have n equals 5, we'd have 25 orbitals. How many electrons can you put in those orbitals? is 2n squared because of the spin. So we will, again, the spin is not supposed to take place until next chapter, but I like to include it now. How are we doing so far? Questions with this one? And this is just using these rules here. Principal, angular momentum, magnetic, and not spin yet, but do that. Questions? All right. So one of these is erroneous. Which one and why? So these sets of quantum numbers specify an orbital. One set is not possible. Which one and why? So if n equals 3, L can be 0, 1, or 2. L being 0 is fine. If L is 0, M sub L has to be 0. Okay, that's good. B, n equals 2. L can be 0, 1. 0 or 1. L being 1 is fine. M sub L can be -1, 0, or 1. Being -1 is fine. That's good. This one here, n equals 1. L has to be 0. If L is 0, M sub L has to be 0. So that's good too. Here we have n equals 4. L can be 0, 1, 2, or 3. L being 1 is fine. If L is 1, M sub L has to be -1, 0, or 1. It can't be -2. So now I know we just showed in this previous example that with n equals 4, we can have M sub L be -2, right? It's in two places, right? It's here and here. We're like, how is that possible? It can't be there. It's because L is 1. L is what bounds M sub L. So in the fourth principal quantum number, you can have M sub L be -2. That's only when L is 2 or 3. When it's 1, it has to be -1, 0, or 1. Does that make sense? Okay. Which one of these is wrong? How many think A? How many think B? How many think C? How many think D? Okay, so more than half the class is going for D. That is the right answer. Because if L is 1, M sub L has to be -1, 0, or 1. So if no one does anybody have any questions? All right. How you feeling? You feeling all right? Pretty trippy? All right, so excitation and relaxation. So does anybody have a favorite TV show? I like Game of Thrones, probably my favorite. Is that good? Anybody have a better TV show than Game of Thrones? No one? Okay. Let us say that we are having a Game of Thrones party. And you guys are all invited, so you come to my house. And in front of the TV, I have this super sweet lazy boy. And then behind the TV, I have a comfy couch. And then behind that, I've got your chairs that you're sitting on there. So if you're the first one to the party, where do you sit? I'm going to go to the lazy boy. So I've been told I look sunburned today. I'll be pink. So there is pink me on the lazy boy. So then more people show up to the party, and they start sitting in the other spots there. So what's going to happen if I might delete everything. Okay, there we go. What's going to happen if I get up to go to the bathroom? Is that seat going to sit there? And I don't say seat check or anything like that. And say I take a really long time in the bathroom, like Mike's not coming back. right? What's going to happen to that seat? Someone's going to nab it, right? And nab it. You're going to grab the seat, and what do? You've been sitting in a chair. Maybe you're even worse. Maybe you're even standing room only in the back. What's going to happen when you sit in that lazy boy? You're going to relax. You're like, I'm going to relax. Okay, so let's take this analogy. Instead of a TV set, let's say we have the atomic nucleus, and instead of chairs, we have specific energy levels as predicted by the Schrödinger wave equation. And let's say it's a hydrogen atom, so it's just one electron there in the ground state in the 1s orbital. And so you can energize, you can shoot this electron up to a higher orbital. So how can you move an electron up to a higher orbital? You can do it by hitting electricity. That's how these lamps work. There's mercury vapor in them, and we're shooting lightning bolts through it, electronic discharge. So we're hitting it with electricity. You can use electron discharge to shoot up electrons at higher energy levels. You can do it with chemical reactions. So chemical reactions may promote an electron at a higher energy level. You can do it with heat. So you can take put a flame in it, like take something, you can stick it into a Bunsen burner flame. That'll excite things up. Also radiation. You can hit it with radiation. Electromagnetic radiation, most likely visible light for electrons, will excite them. So that's called excitation. So, right, you're like, excitation! Higher energy! You're excited, you go high in energy. Excitation is high energy. And then when it goes back down, it's relaxation. You relax down. Okay, so other thing, what if I told you I want you to do the same thing for 12 hours straight? I was like, I want you to do something for 12 hours straight, and it can only be one thing, you can't change it. What would you do for 12 hours straight? No one wants to play with me today. Most people say lying down or sleeping. Well, I'm going to do something for 12 hours, I can only do that one thing. Give me some pills and let me sleep for 12 hours. Kind of thing. No one's going to say, you know what I want to do for 12 hours? I want to climb stairs with 50 pounds on my back. That sounds awesome. So why do you pick, if you're going to do something for a very long time, why do you pick that? You pick the lowest energy because the other reason for that is actually the second law of thermodynamics. The reason why we do this is because of entropy. But electrons do it the same way. Electrons go to the lowest energy states because having the energy out somewhere else actually increases the entropy of the universe. So it makes the energy less concentrated. If you have electrons in higher energies, it concentrates energy to the atom. Having the electrons in lower energy sends the energy out of the atom, and then sending it out can populate state. So it's much more, by probability, it's better to be lower energy. So, but it's kind of intuitive though. Electrons are just like humans. We'd rather be in a low energy state if we're going to do something for a very long time. So electrons will prefer to be in the ground state, in the relaxed state, if you will. So if an electron is promoted to an excited state, it will relax down to various states. And that's kind of what I'm describing here. So, and energy is conserved, right? So we're saying electrons relax, and they do go into lower energy, but energy has to be conserved. So what happens to that energy change? It's emitted as radiation. In this case, visible light, most frequently. And here is the hydrogen atom spectrum right here. The y-axis up here is just potential energy. So up at the top, at n equals infinity, that's a zero potential energy. So that's a free electron. And n equals 1, this is the most bound. This is the most negative potential energy of the electron. So remember, negative potential energy is the bound electron. So, and for the hydrogen atom, electrons going from any state down to the n equals 1 level, this is known as the Lyman series. These are all ultraviolet photons that are emitted. To the n equals 2 level, that is known as the Balmer series, and there's 3 visible wavelengths there. So the hydrogen atom actually, so these 3 wavelengths are what's emitted from the hydrogen atom. And you can see the other ones, there's also smaller transitions, those are infrared. And remember when I said, infrared causes molecules to vibrate? That's true, but infrared can also be lower energy electronic transitions as well. So it's not bad. And I said that all visible light is in the electronic transitions. You can get some ultralight as well. So it's not like there's some fuzziness in that, right? What's like come to my class when I tell you like this is how things are. I'm like, and here's some exceptions. And there's some exceptions to those exceptions. That's the nature of chemistry. That's the other thing that people don't like about chemistry. There's exceptions to the rules, and there's exceptions to those exceptions, and sometimes there's special cases where there's another exception exists, right? Fun stuff. I think it's fun. But here's the visible wavelengths. And if you remember last class, we talked about humans and our eyes, that we're not spectrometers. And if you can you see this on here? The hydrogen spectrum is right here on this side. Actually, there's 4 lines. So there are 3. There are 4 lines there for the hydrogen atom, and it's if you look at hydrogen, it's kind of a pink fuchsia color. Does this have a picture of the hydrogen? No, it doesn't. Okay, I should have brought one. Search the web for hydrogen discharge tube.
Okay, I found this on the web for hydrogen discharge tube.
Okay, do they have it for hydrogen? No. Okay, noble gas. No, not noble gas. Oh, here we go. So this one on the far left, this is hydrogen. So our eyes, though, we're not spectrometers. We take the signal from all the wavelengths and we jumble it together, and it looks pink to us. It looks pink to me. So if we had better eyes, we could see the individual wavelengths, but we don't. We just see them as a signal of our 3, maybe 4 cones. Depends on how lucky you are. Okay, how are we doing? Anybody have any questions? Do you understand this? How this works? That an electron is excited up and to excited energy state. It's called excitation when it's high energy. And when it goes down energy, that's relaxation. It relaxes down. As it relaxes, it emits the change in energy as a photon. Okay. Questions? No questions? Okay. Determine the wavelength of light emitted to an electron goes from n equals 6 to an n equals 5. And the equation I mentioned before is the change in energy level of that is minus the Rydberg constant, Rydberg being 2.18 times 10 to the minus 18 joules. And the energy level, the E to the n is minus Rydberg 1 over n squared. And the delta n is n final minus n initial. So we go from the final, the n equals 5, minus the initial, n equals 6. So we do that. So the delta E, we have to do 2 problems here. We have minus the Rydberg constant, 1 over, so final is 5, 1 over 5 squared minus 1 over 6 squared. And you could I'll probably put this in my calculator. 1 over 5 squared is 1 over 25. I'm going to write this. 1 over 25 minus 1 over 36. Then we could find the lowest common denominator, which would have to be 30. Oh, no, sorry, 36. I'm sorry. It would be 30 squared, so that would be a big number. I don't really want to do that. But let's look at the numbers. So 1 over 25 minus 1 over 36. Is 1 over 25 minus 1 over 36, is this a positive number or a negative number? This is the kind of stuff they ask you on the GRE math, by the way. You have to be able to do this kind of reasoning. So what do you think? This is a positive number. Okay, so because 36 is a bigger number, so 1 over 25 is a bigger number because this denominator is bigger. 36 is a bigger number, so 1 divided by 36 is smaller than 1 over 25. So this is a positive number. And then the minus, the whole thing is a negative number. And you can look at it this way. The electron is losing potential energy. So actually, no, it's gaining. I'm sorry. It's gaining potential energy. It's going from n equals 6. N emitted. I should go the other way. N equals 6 to an orbital, and n equals 5. Oh, from an orbital. Oh, this thing is written backwards. Right? So it should be going from 5, and n equals 6 to an orbital. Oh, I didn't know about that. Anyways, let's go through the math. So now we have, well, either way, we have the change in energy. And remember the formulas for wavelength. Energy is equal to h nu equals hc over lambda, and which then implies lambda is equal to hc over energy. Remember doing those in the previous lecture? So we can put these in. Our wavelength is equal to Planck's constant times the speed of light all over the energy, which is going to be the positive Rydberg number 1 over 25 minus 1 over 36. And the idea here is, why did I switch the signs? Well, the electron is losing energy, but then the loss of the energy, the loss of the electron energy becomes positive energy of the photon. That makes sense. Just like the system argument in quantum mechanics, or quantum mechanics, in thermochemistry, right? So if I'm the system and the energy is leaving me, I'm exothermic. If the system is a system, it's receiving the energy flow is positive. Depends on which way you look at it. This way, the electron is losing potential energy, but then the potential energy is then turned into the photon's energy. So that's the positive number there. And then you just have to put in the numbers. I like to do this all, like the math, all in one step. Then you put 6.626 times 10 to the minus 34 joule seconds times 3 times 10 to the 8 meters per second, all over Rydberg constant 2.18 times 10 to the minus 18 joules, and then 1 over 25 minus 1 over 36. And the n is dimensionless. But if you look at the units, joules cancel, seconds cancel, and you're left with meters. So let me go ahead and do that. 0.626 e minus 34 times 3d8 divided by 2.18 e minus 18 divided by by my calculator, I get 7.46 times 10 to the minus 6 meters, which also equals 7460 nanometers. All right. So tough problem. Recap. We have our equation here. Change in energy for the electron energy is minus the Rydberg constant times 1 over n final squared minus 1 over initial squared. That just comes from the final minus initial from the Schrodinger wave equation. The hydrogen atom solution of that. And the delta energy is 1 over 5 squared minus 1 over 6 squared. Transferring the energy of the photon to get rid of the negative sign. And we have the energy of the photon is hc over lambda, which you can solve for lambda being hc over energy. So we plug that in. H is Planck's constant. C is speed of light. The change in energy, the energy is up there, and from that we get 7,460 nanometers. Questions with this one? All right, your turn. And I'll make it easier on you. What is the energy of the photon emitted as it goes from the n equals 3 to the n equals 1 level? It's more bound. So what is 1 minus 1/9? So how many people think the answer is A, 1/9 Rydberg? How many think it's B, 2/3? I think C, 8/9. Okay, so half a class is going for 8/9. That is the correct answer. And the reason for that is because final is 3, so minus initial. I'm sorry. Final is 1 minus initial. So 1 over 1 squared is 1, and 1 over 3. The initial is 3, so 1 over 3 squared is 9. So 1 minus 1/9. That's 9/9 minus 1/9, or 8/9. Questions with that? Okay. All right, so I mentioned some of these orbital shapes, that we have this integral from negative infinity to infinity of the wave function times complex conjugate over all space. And when you do that, this is what you get. You get an s orbital that looks like this. You get a s orbital. It's a sphere with a much more density at the center of you. So if you do the side star for the 1s orbital, you get this looking thing with a lot of density at the center, and then decreasing as it goes out. And the probability density has an asymptote. So the y-axis is the probability density. It approaches infinity near the origin, and then As radius goes out, it decreases. But then, if you look at the radial distribution function, meaning how much space is actually there, and you apply kind of it's called the shell model. So it's like atoms are like onions or ogres, if you like Shrek. They're layered, right? So if you take the radial function and you integrate it over as shells, you get this part right here, where you get the the y-axis is the probability, x-axis is the distance to the nucleus, and you get a maximum, but then it quickly tails off to basically nothing out here. But something you might have learned in high school, if you study chemistry in high school, they tell you that in the nucleus you have the protons and the neutrons, and the electron cloud you have the electrons, and in the nucleus of the atom there is no electrons. Well, guess what? There are electrons in the nucleus of an atom. So specifically the 1s orbital. The 1s orbital here has a bit of, close to the origin, there is some probability there. Of all the orbitals though, the 1s has the largest amount in the nucleus. So that's another weird thing about quantum mechanics. You can have electrons in the nucleus of an atom. There's not much density, and I call it electron density. The amount of time and space, if you will, that it devotes itself to the nucleus is very small, because nuclei are tiny. But this is one of the reasons why different isotopes have different energy levels. Actually, well, that's the reason why. If you were to look at the atomic spectra for hydrogen, so hydrogen is one proton, is called protium, usually it's called hydrogen. We also have heavy hydrogens, a proton and neutron, that's called deuterium, and then there's hydrogen with 2 neutrons called tritium. And the energy levels are slightly different, and it's because of this effect here. After hydrogen, though, the effect gets much less pronounced, so it doesn't really affect too much. But instead of using electrons, there's other particles, there's other fermions other than electrons. There's something called muons, and you can make muonic atoms. So put a muon around the nucleus, and muons are much heavier than electrons. And then because of that, there's much more density of the muon inside the nucleus. And then so that's one of the studies that they've done, is look at muonic atoms and then look at isotopic effects of the different atoms with that. But of course, that's advanced particle physics. I think it's cool. But all right, back to chemistry. So there is some electron density in the nucleus, but the S wave function as well is also always positive. We'll talk about the sign of wave functions later. And I guess the shut up alarm is about to go off. Here are the other shapes we'll pick up next time. We'll talk a little about the sign of the wave functions, and we'll talk about the other shapes, and we'll finish there. So, okay. Anybody have any quick questions? Nope. Okay. I'll see you on Wednesday.